Recording. Okay. So, I guess just go ahead and start the interview right away.
Well,
If
okay.
you've got the Google Docs right open.
I hope you have a good afternoon.
Let's skip all the semantics. I don't really care.
Oops, did I? Oh, wait, I think I'm going to close. Oh, no, I didn't close it. I found it. Okay, let me share my screen. Enter. Okay, so now the recording sees my screen. Okay.
All right, so this is how it's going to work. You're looking at the Google Docs right now?
I am looking at the Google Docs.
All right, I'm going to release the question. So here's what your problem is. You're in a world full of interconnected cities. A number of n cities are connected so that information is shared and sent between them. Each connection from one city to another comes with a cost, a weight, if you will. It's a graph. It is basically. One city, well, here's the problem here. One city needs to send data to all the other cities. And the problem is that each city can only send the data package once per day. So only one transfer can be done by any one city per day. So what method would you need to use, what algorithm, for the data to be received by all the cities in one day? You need to figure out a path, if you will. And so what would be the cost of such a transfer as well? So in this case, you can assume that the cost in between every one of these connections is an integer, and the total cost should also be an integer. So in short,
the Discord notification. Yes, please going.
In short, you should write a function that returns an int and takes as input a graph implemented as an adjacency list. I might as well write that here.
Return. Graph, so the graph class has it.
A graph implemented as adjacency list vector. It's simply a two-dimensional vector holding a pair of int.
Adjacency list. Okay.
You're also given the int num vertices. And so this is it. You must find a function that will give you a path from the source city to all the other cities using this limitation that only one data package can be sent per day. And in short, find the total cost of such a transfer. Please.
Well, so the problem is that each city can only send one package per day, meaning they can only be reached once. And obviously, because they have a weight, it would be much better to find the path through the cities where the least amount of weight, the distance, the weight for each transfer is not as big, or else that's kind of wasteful.
Yes.
So that
that is how computer scientists think, using the minimum path of resistance.
Exactly. So, well, this sounds like a graph algorithm question, and well, one that I can think of that requires you starting from a source and going through every single graph vector of the vertex, you could say. Well, that sounds like the Prim's algorithm.
I've never heard of that one. Please enlighten me.
Well, I will show you how it works. So I will start by writing the method head. So it returns an int. So we'll start with that, and we'll say, well, because it's prims, I'm going to call it prim algorithm, and it's going to take in that graph. I'm assuming I'm receiving the graph. We're just going to call it graph, and because I don't know the details about how.
You can use C++, Java,
of course,
pseudocode, whatever.
And I'm going to probably be receiving a source.
Yes.
And that's going to be in the form of an integer. Call it source. Okay. So in this case, the first thing I would like to do, I will probably be sorting out the way I will be keeping track of what's visited and not with some sets. So I will make a set of integers called visited for v, and then set of integers not visited called not visited. So right off the bat, I want to insert all of the vertices into the set. So can I assume that because the graph adjacency list is in the form of a vector-vector pair of ints, the integer source is going to refer, so each of these cities,
Mhm.
I'm assuming they're going to have an integer value 0 through 0, 1, 2, 3, 4, 5, 0 through
Yes.
6.
Okay. You're seeing names, but every city is assigned an ID from 0 to n-1 number of cities.
Okay, thank you. I just wanted to confirm that. So in that case, the first thing I'm going to do is add into the set of ints. And then because graph has a num vertices, I'm going to so simply what I'm doing is I'm adding every single possible vertex into this not found. It's the not visited. So n v.
Let me interrupt you for a second. What is the graph dot number? Oh, you must have meant a bracket there, right?
Oh, well, I assumed num vertices is a variable inside a graph.
In class.
Like the graph object has num vertices.
I see, yes.
Yeah, so I'm just, I know it's going to be, well, 0, 1, it's going to be 1, 2, 3, 4, 5, 6, 7, minus 1 is 6. So 0 through 6, insert into the set, we're going to insert I. So now, not visited has 0, 1, 2, 3, 4, 5, and 6. Now we're going to, because source is source, I'm going to v dot insert source, because it's visited right now. We're going to start with it, and then not visited. I don't remember. I believe it's erase, actually. The name of the function for removing something from a set, I believe, is erase. I apologize if it isn't.
For now, this is something you can, of course, look
yes,
up
of course.
in documentation. I'm sure you can do that
later on. But I remember, because I originally thought it was, I write remove often when I was writing it myself, and it would not work.
What do you assume erase is doing here? It's simply removing the
I'm removing source from not visited is what's happening right now, because it is now being visited because we're starting with it. So, and then I'm going to say while the not visited empty, saying I'm going to be iterating this while it is not empty. So now what I want to do is I want to look at all of the edges of the source, which is going to be the top value. Well, let me see. Won't be the top value, but what I can do, well, okay, let me think. I'm gonna start writing, but I might change something. I know right now, so I know my source, I'm dealing with one thing at a time while it's empty, while not visited is empty. Oh yeah, I'm going to be iterating through visited, because visited means it is the stuff. Okay, so now I'm going to go int. I already have an I believe. Oh, well, it's not being used anymore. For int I equals v dot begin. I is less than v dot end. Oh, it should be auto. I plus plus. So now this is a going through the for loop of all of the vertexes that are considered a part of the sorted section, which right now, of course, is just source, but that's okay. Then for each of those, we want to look at all of its possible adjacencies. So we need another for loop inside of it. For auto, we'll call it J equals, now we're iterating through its pairs only. So the graph adjacency list at I, because yeah, so I'm gonna actually need a variable up here that's going to be int small. We'll just call it int small. Oh, we're gonna make it set it equal to the high value, int max. So we don't have to worry about that. It's gonna be set to int max every single time. For convenience, I'm moving this all down here so I can see it all. So now graph adjacent list I, J does not, oh wait, auto J is the adjacency beginning of that because it's the vertex. It is that, the vector, I mean, at that value. J does not equal graph dot adjacency list at I dot end, J plus plus. So that now we are going through, J is now a pair of the to value and the weight. So we're going to be looking for the lowest weight out of all of these weights. So all we're going to do for this part is we're going to check if small is greater than J's second value, which is just the weight of any possible of those combinations. If it is, in that case, small now equals J second, and I need to keep track, actually, I need to keep track of which for value that to value is. So I might just have a little int up here called int to vert, which is just going to equal nothing right now, it doesn't matter. So now the to vert equals J's first, because that is the value that the I goes to, whichever I, oh, I should keep track of the I as well. So I'm going to have an int from vert, and that's going to equal whatever I is at that time. From vert equals I. So now we know out of all of the possible things that are inside of visited, this, as long as the NV is not empty, we are going through and finding the smallest weight to that city. So let's say, you know, if this is 0 and this is a 1 and this is a 3, this pair is now taken into consideration. And now this one needs to end up joining V, which is my to vert. So once this whole for loop is over, I now need to do visited.insert to vertex, because it's joining the little party of, you know, ones that are highlighted, you could say. And now I need to remove it from not visited. And you want the weight. So I can kind of make this anywhere. I'm just going to have int total weight somewhere. I'll make it before the while loop because it doesn't matter. Oops. We're going to have an int total weight equals 0. So now we're gonna say total weight plus equals small. Because now it's starting to add up that pathway all the way to the very last value. And we're removing NV, so yeah, that's how it goes down. And after that while loop, we're just going to return total weight, because that is the value it's seeking, I believe. It's the returns the int of the weight, yeah, and what will be the cost. I think that's it. I'm being honest.
I will point out this is a minor thing. I'm sure you would have found it. There is a slight problem with your not visited instantiation loop.
My not visited, huh? Which one?
You see where it's the for loop you have, which inserts, which is supposed to insert every node.
Oh, this one, yes.
It's just a simple thing. This would unfortunately be one too short for the non-visited set.
0. Oh, well, oh, I see what you mean. Yes, it would have been figured out eventually because it's not less than. So yes, it would have just went 0, 1, 2, 3, 4, 5, 6. Thank you for that.
That's fine. And I'm looking at your code right now, and I must say I have to commend you for just very clear variable names, and a lot of them, rather, you make a lot of variables that I'm sure make this code very easy to implement and modify.
Thank you.
And otherwise, looking at it right now, all the brackets seem well. There's no problem with the syntax.
Yeah, sorry, it breaks off into the next page, but it's still all together.
The only thing I could recommend is simply just adding comments. That could always help, adding documentation.
Oh, absolutely. Yes, you're very right.
Again, that was never a requirement for the for this interview, but otherwise, no. So what you've created here is, what would you call this kind of this new graph that you've created? There's a word for it.
What would I call this graph?
There's this path that you've created using the Prim's algorithm as a name. Do you know what it's called?
Oh, it is the least weighted path.
It's something about a tree.
Something about a tree.
A minimum spanning tree is what these are called.
Ah, yes, MST, minimum spanning tree. I'm sorry, I was trying to understand you, but yes, of course, this is a minimum spanning tree because it is going.
So you were aware. Maybe I phrased my question badly.
No, that is okay. Yes, of course, because a tree, it is a type of graph.
I see. Very well, very well. So what do you v dot insert and v dot erase. From simply looking at your code, you're indeed erasing. So at one point this while loop will end. The total weight is updated every time. Visited is always inserted.
I did just realize that theoretically I don't need to keep track of the from vertex because I never use it. Because it's just, well, it's never used because, because I end up saving the value, I just realized, as small, and then you add it in.
So this is one of those cases where even though for the sake of the algorithm, the variable isn't actually useful, it can always be used as simple documentation for a cout, for example.
Yes, of course. I can say, it is the weight ends up being from blank to blank using that value. Yes, of course. In this case, it's never used, but that is a good observation.
And even in this case, it is such a minor memory that someone might have left it. Well, it would seem this would indeed return the the minimum direction from a source node to every other node while passing through them only once. I do believe that is that is a successful minimum spanning tree.
Thank you.
Congratulations.
Did I get the job?
Unfortunately, we have no more spots for you today, but
Dang.
well, thank you for this interview.
Thank you for interviewing me upon knowing there were no more spots. I really appreciate that.
I'm obliged to. Okay, well, thank you. Have a good night.
You too. Good night.